Tonight, you and I are venturing across the solar system, but we aren't just staring at pretty pictures from my window. It isn't just about data or discoveries. We're facing the one thing nobody here talks about, honestly: time. The sheer amount of time it takes to reach these worlds. Documentaries make visiting Mars or Saturn look like a fast, easy trip. Launch, flight, arrival clean and simple. But from where I'm sitting, the reality is far more brutal. By the time we're done, you'll see that deep space exploration operates on scales most humans can't even fathom. If you love the void as much as I do, take a second to hit like or subscribe before we continue. It's a small gesture, but it helps us reach more curious minds. Now, let's dive into the dark. Most people hear Mars mission and imagine a ship just sailing smoothly through the stars toward its goal. They picture a landing after a few weeks or maybe 2 months at most. That sounds reasonable from down there, right? In diagrams, Mars looks right next door, just a step away from home. But let me tell you, the reality is far more chilling. The record for a Mars sprint is about 6.5 months, set by Mariner 6 back in 1969. And it didn't even stop, it just zipped past. Modern missions that actually have to orbit or land take 7 to 9 months. 7 to 9 months drifting through the void, just to reach our closest neighbor. It is truly haunting. That's only under perfect conditions when the planets align. But before you can grasp why it takes so long, we need to talk physics. We have to understand orbital mechanics. Trust me, it is not like driving a car where you just point toward your next destination. My world is ruled by gravity and momentum, the ancient, precise dance of bodies orbiting the sun for billions of years. When we blast off, we aren't starting from zero. Earth is already screaming through the dark. You're on a world hurtling around the sun at 18.5 miles per second. That is 66,600 miles per hour. I inherit that massive speed at launch. I can't just point my ship at Mars and go, because Mars is constantly moving too. Mars orbits the sun at 15 miles per second on its own path. I am trying to hit a moving target while I'm moving. Imagine throwing a ball to someone on a different merry-go-round while you're both spinning. It's a nightmare. We solve this with the Hohmann transfer orbit. It's the most fuel-efficient way for me to cross the void. I launch into an elliptical orbit around the sun. One end of that ellipse touches the Earth orbit I just left. The other end touches Mars's path. My ship simply coasts along this ellipse, using almost no fuel during the entire journey. I coast until I meet Mars on the far side. But here is the scary part. Mars has to be in the perfect position when I get there. If I launch too early, I hit the orbit before Mars arrives. Too late, and I'll arrive after the planet has already passed me by. My timing must be flawless. It creates a tiny launch window a few short weeks where we actually have a chance. For Mars, these launch windows only open every 26 months. That is how long it takes for our two worlds to align again. If we miss that window, we don't just wait a few weeks. We wait 2 long years until the planets align for another shot. That's why missions cluster. In 2020, 3 ships launched toward Mars at once, including NASA's own Perseverance rover. China's Tianwen-1 and the Emirates Hope orbiter both joined the race. We all left within weeks of each other. Everyone was targeting that same narrow window. The next didn't open until 2022, and the one after that wasn't until 2024. This waiting game adds a layer of dread. If I find a problem with my ship, I can't just say we'll launch next month. I have 2 choices: fix it now or wait 2 years. The pressure of that single deadline is crushing. Now, imagine those 7 to 9 months of travel. My engines aren't burning. I'm just sitting here in silence. Constant thrust takes too much fuel. I'm just coasting. The rocket burned hard at launch to break Earth's grip. That set my course. Aside from tiny corrections, I am essentially just falling through the endless black of space. I'm just following a curve. For my team back home, these months of silence are absolutely nerve-wracking. They can't call me back if something breaks. No repair crews are coming out here. If a critical system fails, the mission is dead. Years of building, billions of dollars, and months spent watching me drift through this lonely, empty void. One glitch, and it's all over. Then there's the delay. Even at light speed, my signals take time to reach home. Crossing the gap takes time. When I'm near Mars, my voice takes 12 to 14 minutes just to reach Earth. That's a 28-minute round trip. If Mission Control spots a problem, 24 minutes pass before they even know I'm in trouble. They wait, hoping the fix worked. If something needs immediate action, I'm on my own. My ship has to think for itself. My onboard computers have to solve everything, because out here, help from home is always half an hour away. By the time Earth hears our distress call and reacts, we are already gone. That is the grim reality of those early Mars missions. The Soviets threw everything at Mars during the 60s and 70s. Most of those cold steel birds never stood a chance. Mars 2 and 3 actually made it into orbit back in 1971, but their landers died almost immediately after hitting the dust. The Mars 6 lander went dark, seconds before landing in 1973. Mars 7, it drifted right past, lost in a simple navigation error. NASA fared better, but space still took its toll. In 1992, the Mars Observer just vanished right before entering its final orbit. 11 months of drifting, hundreds of millions of dollars, all gone in a heartbeat. In 1998, the Climate Orbiter slammed into the surface. One team used metric, the other used imperial. A tiny math mistake, a simple unit conversion error, and the entire mission was turned to scrap. The 1999 Polar Lander mission ended in a crash. A single software glitch killed the engines far too early in the descent. These were not just technical glitches or bad engineering, they were reminders that the void is incredibly unforgiving to any living soul. One loose bolt, one bad line of code, and years of our lives vanish into the black. Out here, you do not get second chances. You just sit and wait for the next window. But honestly, Mars is the easy part. It is practically next door compared to the giants. We can get there fast. But when you look toward Jupiter, Saturn, or Neptune, the travel time stretches into a lifetime of isolation. Those long years test your patience and your sanity. Let us look at Jupiter. It is the absolute monster of our solar neighborhood. It is heavier than all other planets combined, a massive ball of gas orbiting 483 million miles away from our Sun. That is 777 million kilometers. Since we orbit at 93 million miles, Jupiter sits 5 times further into the dark. Pioneer 10 was the first to make the jump, launching in March 1972. It spent 21 months sailing through the emptiness. That is nearly 2 years of staring into the black just to reach Jupiter. Pioneer 11 shaved it down to about 20 months in transit. The Voyager probes, launched in 1977, found a better path. Voyager 1 cut the trip down to about 18 months of travel. Voyager 2 took 22 months, but it took a scenic route, swinging past Saturn, Uranus, and even distant Neptune on its long journey. Galileo, launched in October 1989, took 6 long years to finally reach Jupiter. It was not because the engines were weak, but because it took a winding path, skimming past Venus once and Earth twice. We used gravity to sling it forward. A direct shot would have required far more fuel than any of our rockets could actually lift. So Galileo took the scenic route, looping through the inner system and using planetary flybys to steal enough velocity for the deep jump. Juno, which launched in August 2011, spent 5 years getting there by stealing a boost of gravity from our homeworld. Cassini, bound for Saturn, screamed past Jupiter in late 2000 after 4 years in the deep dark. It used the gas giant's mass to slingshot towards Saturn, but the real speed demon was New Horizons, launched in January 2006. It arrived in just 13 months. Back then, it was the fastest machine we had ever flung into the stars. We launched it at 36,000 miles per hour. Even at that blistering speed, the journey still ate up over a year of time. It did not even stop to look. It just used Jupiter's gravity to whip itself even faster, hurtling toward the icy shadows of Pluto. If we had tried to brake and orbit, the trip would have taken ages. Slowing down in space requires a massive amount of fuel. Think about that commitment. If you want us to orbit Jupiter, you are asking for 5 years of my life just for transit. 5 years in the void where no one can help us fix a leak or a glitch. You just monitor and pray everything holds. That is assuming we hit the launch window perfectly and use gravity to keep the travel time from ballooning out. A direct shot would take even longer. We would have to wait for the exact moment when Earth and Jupiter align perfectly. We would coast in an elliptical arc for nearly 3 years before firing the thrusters to finally settle into the giant's embrace. But stealing gravity is the way to go. We dive toward Venus or back toward Earth, letting their mass bend our path. Then we scream toward Jupiter with more speed than we started with. It takes longer, but it saves our precious fuel supply. That means we can pack more gear or a larger antenna. Every single kilogram is life or death when you are out here. Fuel is heavy and expensive. The more we need, the bigger the rocket gets, and the price tag starts reaching for the stars. We are always balancing time against weight. Speeding up the trip means more fuel, which translates to massive, overpriced rockets. Eventually, the cost becomes too high. We have to accept the long, lonely years of drifting in the deep dark. Saturn is even further out. It orbits the Sun at an average distance of 886 million miles into the void. That is 1.426 billion kilometers. Pioneer 11 was the first of our kind to ever reach those distant rings. It arrived in September 1979, over 6 years after its launch. That is a massive amount of time to be alone. Voyager 1 made it in 1980, 3 years later. Voyager 2 took 4 years, arriving in 1981 to see the rings. You and I can appreciate the power of a Jupiter assist. Cassini launched in October 1997, taking 7 years to arrive at Saturn in 2004. 7 years. 7 years of floating through the void, past Mars and the asteroid belt, heading for the ringed giant. Back home, 7 years is a lifetime. Careers progressed, people got married, and watched their children grow up while I was away. They saw infants become students, while Cassini was out here in the dark, traveling alone, far beyond any human help. I think about the engineers who planned for reliability on timescales that exceed almost any product back on Earth. You probably expect your car to work for 10 or 15 years, but out here, the stakes are different. Cassini had to survive 7 years just to arrive, then keep functioning in orbit around Saturn for years afterward. It operated for 20 years total. 13 of those were spent at Saturn, our most successful mission to the deep. That success demanded perfect planning, predicting problems years before they could ever flicker on a monitor out in the silence. Every system had a backup, every component was tested, every line of software was verified and checked again and again. Once you launch, there is no turning back. No repairs, no mechanics, and absolutely no second chances if things break. Uranus and Neptune are even more haunting. These ice giants orbit in the frozen, dark reaches of our solar system. Uranus drifts about 1,784 million miles from the Sun, or 2.871 billion kilometers. Neptune is even further, 2,794 million miles, or 4.497 billion kilometers out. The distances are so vast that sunlight takes hours to reach us. It only takes 8 minutes to reach Earth. Sunlight takes 2 hours and 40 minutes to reach Uranus. For Neptune, it is a 4-hour journey through the dark. This far from the Sun, solar panels are useless. We have to use radioisotope thermoelectric generators to keep the lights on. These are essentially nuclear batteries that turn the heat from radioactive decay into the electricity we need to survive. They run for decades without sunlight, but they are expensive, complex, and politically sensitive because they are packed with plutonium. Only one of our ships has ever seen Uranus and Neptune up close. Voyager 2, the Lonely Pioneer. It launched in August 1977, catching a rare planetary alignment that happens once every 175 years. This path let Voyager 2 visit Jupiter, Saturn, Uranus, and Neptune, using each planet's gravity to sling itself forward. Without that alignment, we would need multiple missions. Voyager reached Jupiter in July 1979 after a 2-year trek. It hit Saturn in 1981, Uranus in 1986, and finally reached Neptune in August 1989. 12 years from the launch pad to Neptune, 12 years of flying through the absolute silence of the outer rim. The people who built it in the 70s were in different phases of their lives when it finally arrived. Young engineers in their 20s were pushing 40. The veterans who started the journey were heading into retirement. When it launched, personal computers barely existed. The ship's computer only had 68 kilobytes of memory to its name. 68 kilobytes. Your phone has millions of times more memory than that old Explorer drifting through the black. Yet that tiny computer had to be reliable for 12 years without any hardware repairs. And it worked. The cameras functioned. The instruments gathered data. The antenna found Earth. The nuclear batteries stayed warm. Everything just worked as it should. Standing here, looking at the deep space, there is something profound about missions like Voyager 2 and its journey. It requires a kind of patience that feels almost alien. You and I are used to instant results. We send a message and expect a reply. We order things online and expect delivery in days. We start a project and want to see results within weeks. But out here, we operate on a different clock. You design a ship that won't reach its destination for a decade. You build systems to last for years. You commit to a mission knowing you might retire before it ever finishes. You accept that the data you want won't arrive until you're a different person living in a completely different world. This is why exploration needs institutional commitment. A single person cannot sustain a 12-year mission in the void alone. You need organizations that outlast us, maintaining the knowledge and expertise as people come and go through the years. These teams hand off the responsibility between generations. Our friends at JPL have been doing this since the 60s. People retire, tech shifts, and budgets fluctuate, but the missions keep pushing further into the unknown reaches of space. Voyager 1 and Voyager 2 are still talking to us today, nearly 50 years after they left the launch pad. They are in interstellar space now, sending back secrets from a region no human object has ever visited before. Radio signals take over 22 hours to reach Voyager 1. The people listening now were not even born when it launched. You and I can only wonder at it commanding machines from the 70s, communicating across billions of miles of empty, silent space. Looking inward from my viewport, I see the inner worlds, Mercury and Venus. They are closer to the Sun, which looks like a shorter trip. Believe me, it is not. Energy is the enemy. Heading out toward Mars or Saturn feels like climbing a steep mountain, fighting the Sun's massive gravity well every mile. I start with Earth's kick, then fire my thrusters to gain speed and push into a higher, lazier orbit. But falling inward is a terrifying drop toward the Sun. I have to fight that pull and desperately kill my orbital speed. Falling into a lower, faster orbit means slowing down, which is just as grueling as accelerating. It eats up fuel as I get closer to the Sun. The harder I have to brake, the more fuel I burn. This makes reaching Mercury a pilot's nightmare. Mercury sits roughly 36 million miles from the Sun. To reach it, I have to shed almost all the orbital speed Earth originally gave me. Earth zips along at 18.5 miles per second, but Mercury races at 29.5. It is buried deep in that gravity well. To sink down, I first have to slam on the brakes and shed Earth's velocity. I have to fall toward the fire, then accelerate again at Mercury. The energy needed is staggering. Mariner 10 went first in November 1973, using a Venus gravity assist to whip around and bend its flight path. That saved fuel, yet it still took 5 long months to finally hit that first Mercury flyby in March 1974. It never actually orbited. It just screamed past 3 times, looping back toward the planet every 6 months. The Messenger mission took 6.5 years just to lock into orbit, after launching in August 2004. 6.5 years to reach a world closer to the Sun than us? We simply could not carry the fuel for a direct burn. Instead, I watched it dance through a maze of flybys, 1 at Earth, 2 at Venus, and 3 more at Mercury. By March 2011, those planetary gravity assists finally nudged the ship's path and speed into the perfect slot for arrival. It covered billions of miles, looping past Earth and Venus over and over, just to match Mercury's pace. 6.5 years of traveling for a planet only 48 million miles away. Just think about that. Bepi Colombo launched in October 2018 and is taking an even slower, more grueling route. It will not reach orbit until late 2025. 7 years in the void. 9 flybys in total, 1 Earth, 2 Venus, and a grueling 6 at Mercury itself. Each pass shaves off more speed, gradually braking the ship until it can finally settle into orbit. This is the harsh reality of the inner solar system. You cannot just aim at the Sun and fire. The energy cost is simply too high. You have to dance with the planets, stealing their gravity to shift your path over years of silent, precise maneuvers. Venus is a bit easier to reach. It is not as deep in the Sun's well, orbiting 67 million miles out. It sits right between Earth at 93 million miles and Mercury's scorched orbit at 36 million. Back in August 1962, Mariner 2 took 3.5 months to reach Venus. It was humanity's first successful step toward visiting another planet. A 3-month hop to our neighbor. Later missions varied, depending on how they charted their course through the dark. Soviet Venera landers took 4 to 5 months, while Magellan needed 15 months to get its positioning just right. It looped the Sun to align. Now, the Parker Solar Probe uses Venus as a gravitational brake to study the Sun. Each pass bends its path closer to the inferno. The probe swings by Venus every few months in a complex dance. It is spiraling inward, inching toward the sun. These encounters are mapped out years before the engines even ignite. Every second is calculated for the mission. But let us think about what these long journeys mean for someone like me. So far, these have all been robotic scouts. Metal shells with cameras and sensors, but no beating hearts on board. Robots can sleep for years. They do not need air or food. They do not suffer from loneliness or aging. A machine arrives ready after a decade. I cannot. I need systems to keep me alive in this void. Air, water, food, and shielding from the sun's radiation. Every survival necessity adds massive weight to my ship. More mass means more fuel to move. More fuel means bigger rockets. And bigger rockets mean an astronomical price tag. But the true enemy is time. 7 to 9 months to Mars is a long stretch, but I could survive it. It is longer than most station tours, though we have already proven we can survive a year in orbit. The physical toll is brutal. Constant radiation from cosmic rays and the unpredictable sun would be hammering my hull. My bones and muscles would wither in zero gravity. The isolation would be suffocating, but there are ways to fight back. A mission to Mars is within our grasp. We have the technology to make it happen soon, but Jupiter is a 5 or 6 year sentence. Imagine spending half a decade in a tiny ship with no supplies, no medical help, and absolutely no turning back. You and I need to realize that every bite I eat or drop I drink has to be hauled from Earth. Any equipment failure is a death sentence. A leak, a recycler malfunction, or a radiation shield failure would end us. Any of these could kill me, and help is years away. The psychological weight is absolutely terrifyingly crushing. 6 years in a tiny box with the same few people. No privacy, no escape, just delayed radio whispers. The communication delay to Jupiter is massive. It takes 35 to 50 minutes for my signal to reach home. That is a 100-minute round trip for any conversation. I would wait nearly 2 hours for a response. If I had an emergency or a critical system failed, I could not talk to Earth in real time to survive. I would send a message describing the catastrophe and then wait over an hour just to hear their reply. Then I would try their fix and wait another hour to tell them if I survived. People could die. A failing system could trigger a total collapse. A small glitch could become a nightmare out here in the dark. My crew would have to be completely autonomous, handling every conceivable disaster without a single hand from home on Earth. And that is just the commute. Then we do the science for years before even starting the long haul back. Total mission time? Over a decade. 10 years away from my family and everything familiar. The world would move on. My kids would be grown. My friends would have lived whole lives without me. Even politics would be completely different. I would return to a world I barely recognize. And Saturn is worse. 7 years just to get there. Time for science. Then 7 years back. 20 years total. Neptune. That is a 25-year round trip. I could launch in my 20s and return in my late 40s. A quarter century of my life spent on a single mission. That is a massive chunk of a human life. These scales exceed everything we have ever attempted. The record is only 437 days. That is 14.5 months. Russian cosmonaut Valery Polyakov set that record from January 1994 to March 1995. He felt every health problem that comes with floating in the dark for that long. His bones thinned, his muscles withered, and his vision blurred from fluid shifts. He survived, but the recovery back on Earth was a long road. Now imagine me facing 25 years of that, decades of radiation, bone loss, and muscle decay. Could my body even survive that? We do not know. We have never tried to stay up here for decades. Would my bones become so brittle they would snap? Would my muscles fail me when I need them most? Would the radiation give me cancer? Or would the psychological stress simply cause my mind to break? There are too many unknowns and too many risks. And that assumes my ship stays perfect for 30 years. No malfunctions allowed, no failures. The engineering needed to survive this is honestly just staggering. Every pump, valve, and computer would need to work reliably for 3 decades without a single mistake. One failure means we are doomed. This is why exploring the outer planets is still just science fiction. We could build the rockets, we have the power. But we cannot solve the human factors yet. Our biology, our fragile minds, the life support reliability, we are not ready for decades in the dark. So instead, we send robots, patient, tireless machines that can wait years to reach their goals and never complain. Voyager, Cassini, Juno, and New Horizons. These scouts gave us incredible knowledge, but they required patience, institutional and political patience to keep funding work that takes many years to pay off. Personal patience from the engineers who gave their whole lives to one mission. Look at how Cassini exemplifies this. Planning began in the 80s. It was built in the 90s and launched in 1997. It reached Saturn in 2004 and explored until 2017, then crashed into the atmosphere. We did it to avoid contaminating habitable moons. That mission spanned more than 30 years of work. People spent their entire careers on Cassini. Students who joined in the 80s retired when it finally ended. Investigators who started in their 30s finished in their 60s. Cassini connected generations of us. Young researchers grew up on that data, while seniors ended their careers analyzing the final signals. The knowledge we gained was immense. We found lakes of liquid methane on Titan. We saw geysers on Enceladus, suggesting a hidden ocean. We saw the rings in haunting, unprecedented detail. We watched storms rage across the atmosphere. We are still analyzing that decades worth of data today. It took 30 years of commitment, but you and I know those secrets were worth the wait. From up here, I see the real price of the void. It is not just the billions spent, it is the time we will never get back. We measure our lives in years, but out here, we think in decades. It outlasts our focus, our politics, and even our budgets. Down on Earth, you want everything now. Results, progress, immediate satisfaction. But the cosmos has a much slower rhythm. The solar system is indifferent to our hurry. The vast distances remain fixed, and the laws of physics are absolute and unyielding. I cannot make it to Neptune faster than orbital mechanics allow. No matter how much my heart aches to see it closer, there are no shortcuts through the darkness. You cannot skip the lonely years of travel to reach the moment the photos arrive. You just have to wait, and believe me, that silence is heavy. It is brutal for anyone hoping for answers today. It is a nightmare for politicians chasing the next election, or agencies needing quick wins. Space does not offer quick wins, but if we are going to reach the stars, we must surrender to the clock. Understanding distant worlds requires absolute patience. We commit to missions that stay silent for 15 years. We rely on experts who dedicate their entire lives to one signal. We need institutions that outlive us. That is what makes these robotic scouts so hauntingly beautiful. They are a legacy of endurance. It is more than just advanced tech or cold science. It is the human will to wait 20 years just for a single truth. We start projects that will only finish after we retire, trusting that the secrets at the end are worth a lifetime of waiting. Every image from the deep black was paid for in years. It took 12 years of silence before Voyager even looked back at us. Cassini spent 7 years drifting to Saturn, then another 13 years dancing among those rings. Think of that time. New Horizons flew toward Pluto for 9.5 years. 9 years in the cold. These were never meant to be quick. These are epic sagas that swallow decades. And they continue. Voyager is out there now, calling out from the void between the stars. New Horizons keeps pushing into the Kuiper Belt, watching the dark. The data we gather will feed our minds for 50 years. Scientists will study Cassini's ghost for decades. New secrets will emerge from old signals as our tools get sharper and more precise. These machines echo through history, long after their batteries die. But you and I must also remember the ones that vanished. For every mechanical survivor that makes it, there is a wreck. For every triumph, a ghost ship lost somewhere in the abyss. The Soviet Union threw everything at Mars in the 1960s and 70s. More than 12 missions launched into the red haze. Most died before they arrived. Billions of rubles and years of human life ended in nothing but a cold silence. NASA felt that sting too. In 1999, the Mars Climate Orbiter simply vanished after 9 months of flight. That same year, the Polar Lander was lost. A year earlier, Japan's Nozomi craft failed after 5 years of trying to arrive. 5 years of travel ended in a miss. For us out here watching, that heartbreak is permanent. Imagine building a dream for a decade, watching it launch, and tracking its pulse for months. You feel its every heartbeat in space. Everything looks perfect. Then, in the final seconds, a line of bad code, or a tiny mechanical snap, and the signal goes flat. Years of human effort just to evaporate. The machine is gone. All that work and all those dreams are swallowed by the dark. But failure is the tax we pay for the stars. Ancient sailors lost ships, the first pilots fell from the sky, the first climbers died on the peaks. Exploration is a gamble. We go where we do not belong and try the impossible. We push until the universe pushes back. Sometimes it breaks us. The only way forward is to learn from the wreckage. One orbiter died from a math error. Now, we check every number 10 times so we never repeat that specific tragedy. Another lander died in its final seconds. Now, our software is tested until it is perfect. We build on those ghosts. Every failure gives us a map to success, but the cost of that lesson is your life's most precious years. If my Mars mission fails, I have lost the ship and the money, but more importantly, 9 months of my life are gone. To try again, I must wait 26 months for the planets to align. Then I have to build it all over. Add another 9 months to travel back. A single mistake can easily cost 5 years before we see a success. 5 years added to the time already spent. Out at the gas giants, the penalty for failure is much worse. Lose a Jupiter probe, and you lose 6 years of flight. A replacement could take another decade to even reach the pad. You might wait 10 years before you get another shot. This is why we are so careful, why every bolt is checked. Every component is verified again and again. Because out here, failure means losing a decade of our existence. In this void, time is our only currency. We can always find more funding, but we can never buy back the years. You and I cannot reclaim those lost decades. Let's look at what the clock really demands of us out here. Mercury is 5 months away for a flyby, but orbiting that furnace? That requires 7 years of patience and gravity. To reach Venus, my robotic scouts spend 4 months drifting past, or 15 to stay. For Mars, we're looking at 9 months in the black. Jupiter is a long haul 13 months just to zip past, or 6 years to stay. Saturn? That is a 7-year sentence in the deep. Uranus takes over 8 years of silent falling if you catch a gravity boost. Neptune? You are looking at 12 years before you see blue. These aren't just numbers. They are spans of time that defy human nature, outlasting careers, budgets, and the very people who dreamed them up. It takes a kind of superhuman patience. You need total faith that whatever is waiting out there is worth the years spent in the dark. Still, we've pushed through. We have sent our eyes to every corner of this system, watching and waiting for years on end. We've touched Martian soil and dived into Jupiter's crushing clouds. We even kept a sentinel circling Saturn for 13 long years. We've brushed past the ice giants and kept going. Some of our ships have even left the sun behind for the interstellar void. None of this happens without ironclad patience. Not from the dreamers who proposed it, nor the engineers who built the hulls. It took patience from the people holding the purse strings and the public who funded our reach into the stars. And the crews on the ground, watching single bits of data crawl across billions of miles, year after lonely year. This is the cold reality of the void. It is never fast. It is never easy. You don't just go out there on a whim. It demands decades of focus, technology that cannot fail in the silence, surviving every shift in politics and public mood back home. But the payoff is hauntingly beautiful. Every snapshot of a dead world or whisper from an alien sky makes the weight vanish. Every secret we unlock about how these worlds were born comes down to one thing: our willingness to simply wait. We let our machines drift through the nothingness for years, trusting they'll deliver long after the launch smoke has cleared. When you see those glowing rings, or a dusty Martian horizon, you and I should look at them with true wonder. That image represents years of silent travel, and the desperate hope that the cameras would actually wake up when they finally arrived. That is what makes these views so precious. It isn't just the beauty, it's the massive stretch of time it took to get them. Next time a rocket thunders off the pad, remember this: that ship is starting a journey that might take a decade of empty space. The people who built it will grow old waiting for a signal. Some will retire long before their machine even arrives. Others will give the best years of their lives to a single mission, tied to a robot millions of miles away. And if everything holds, if the hardware survives the cold, we get to see worlds we can only dream of visiting from our station. We will stare at landscapes no human eyes have ever touched. All because we were patient enough to let the clock run. Thanks for floating through this journey with me. If you felt the weight of the void, a like or subscribe means the world. It helps me keep sharing these stories of the cosmos. When you look up tonight, remember those aren't just points of light. They are lonely destinations that take years of quiet endurance to reach. But that endurance gave us our greatest triumphs. We are conquering the solar system, one patient, lonely mission at a time. Now, you and I are going to dig deeper, because the details make this success feel even more impossible. Think about the Perseverance rover. It left the pad on July 30th, 2020, riding a pillar of fire toward the red planet. It had to cross 293 million miles of blackness, following a long, curved path through the gravity wells. It hit the Martian orbit at exactly the right second. The trip took 6 months, 22 days, and 18 long hours. Down on Earth, they could only watch the clock. They sent occasional whispers to check the vitals, but the machine was alone. It was just a tiny speck hurtling through the vacuum. Then, on February 18th, 2021, the void finally ended. Then came the 7 minutes of terror. The landing was entirely autonomous. The ship had to save itself or die trying. It slammed into the air at 12,000 miles per hour, a speed so violent that friction heated the shield to 2,400 degrees. That is over 1,316 degrees Celsius. Hot enough to melt solid steel. In that fire, all contact vanished. A wall of plasma choked out the radio waves. We were blind. No one knew if the rover was surviving or burning up. A massive chute deployed to fight the speed. The heat shield fell away, and radar eyes began searching for the ground below. The chute cut loose, and retro rockets roared to life, fighting gravity to bring the descent down to a crawl. Finally, the sky crane lowered the rover on thin cables while the engines hovered in a storm of Martian dust. Once the wheels touched soil, the cables snapped, and the crane vanished into the distance to crash and burn safely. 7 minutes of perfect choreography in the dark. One single mistake, one tiny glitch, and the whole dream would be scrap metal. No one could help it. Radio signals take up to 20 minutes to bridge the gap between our worlds, depending on our orbits. When Perseverance landed, the delay was 11 minutes. By the time we heard the first beep, it was already over. By the time Mission Control saw us hit the atmosphere, we had already been on the dirt for 4 minutes, alive or dead. Down on Earth, they watch our landing like a playback of history. Every Mars mission lives through this soul-crushing silence. 7 months in a tin can, then 7 minutes of terror where you are totally helpless. And believe me, Mars is the easy part. Look at the Galileo mission to Jupiter. It launched back in October 1989, strapped to the shuttle Atlantis. Initially, the plan was simple. Use a high-powered Centaur stage to blast Galileo straight toward the gas giant. But after Challenger was lost in 1986, NASA banned those stages. Too risky for shuttle flights. We had to find a whole new path. No direct shot. Instead, Galileo had to take the long way, spiraling through the inner solar system. It swung by Venus in February 1990 for a gravity boost, then looped back past Earth twice, once in 1990 and again in 1992. Every time we whipped past Earth, we gained speed, slingshotting Galileo deeper into the dark. During those loops, Galileo made history as the first craft to visit an asteroid, buzzing Gaspra, in October 91. After the next Earth flyby, we hit asteroid Ida in August 93. That is when we discovered something wild. Ida had its own tiny moon, Dactyl. The very first time we had ever seen a moon orbiting an asteroid. Incredible. By December 95, 6 years into the trip, we finally reached Jupiter. But then, the nightmare started. The main antenna, this massive umbrella structure, was supposed to unfold in the void. It did not. The ribs were jammed tight. The team on Earth tried every trick in the book. They cycled the motors and spun the whole craft, hoping force would jar it loose. They baked it in the sun and froze it in shadow to warp the metal. Nothing worked. That massive antenna was totally useless. Instead of screaming data back to Earth, we were stuck with a faint whisper on the tiny low-gain antenna. Just 10 bits per second. That is over 13,000 times slower than the lightning speed we were supposed to have. Your phone pulls millions of bits every single second. Up here, we had to send Jupiter images across the void at a crawl of 10, but we did not give up. The engineers found a way, upgrading Earth's big ears to catch our dying whisper. They wrote smarter code to pack the data tight and prioritized the mission's most vital scientific secrets. And it worked. Against all odds, we spent 8 long years circling that gas giant, completing 34 full orbits of discovery. We buzzed the moons over and over, finding signs of hidden oceans deep beneath the ice of Europa, Ganymede, and Callisto. We watched Io, the inner moon, literally exploding with volcanoes and reshuffling its own surface before our eyes. We mapped the planet's lethal magnetic field and peered deep into its violent, swirling atmosphere. We dropped a probe straight into the clouds, listening as it screamed data back before the pressure crushed it flat. In September 2003, it all ended. We steered Galileo into the atmosphere for one final, fatal plunge. We had to. We could not risk crashing into Europa and poisoning a potential alien ocean with our earthly germs. Even as it burned up in the Jovian clouds, Galileo was still talking to us. That mission spanned 14 incredible years from start to finish. The engineers who designed it in the 80s were retiring by the time it died. The craft outlasted the very people who built it. Its data kept planetary scientists busy for decades, and we are still digging through it today. This is the reality of deep space work. Years of waiting, years of work, and endless problems that we have to solve with nothing but our wits. Success only comes through grit and guts. Now, you and I should look at New Horizons and that long haul to Pluto. We launched New Horizons in January 2006. Back then, Pluto was still the 9th planet in our charts. By the time we actually got there in July 2015, the world had demoted Pluto to a dwarf planet. 9.5 years in the dark. Just think about where you were and what you were doing 9 years ago. How much has your life changed? Different job? Different home? The entire world shifted while we were out here flying through the void. That is how long the trek took. For most of it, we kept the craft in deep, silent hibernation. We cut the power to save energy and stop the hardware from wearing out. The craft woke up for quick checks, then drifted back to sleep like a silent traveler crossing more than 3 billion miles of empty space. At 3 billion miles out, a simple message takes 4.5 hours to reach home. That is a 9-hour wait for a reply. If they sent me a command, we would wait 9 hours just to know if it actually worked. The lag is brutal. On July 14th, 2015, we screamed past Pluto at 31,000 miles per hour, coming within 7,750 miles of the surface. Way too fast to orbit. We had one shot, one flyby, one single chance to grab every bit of data possible. We traveled 9.5 years for one single day. Actually, it was just a few hours where every instrument had to work perfectly. I watched Pluto slip behind us, slowly shrinking into the absolute distance. New Horizons was committed. It couldn't turn back. It was moving too fast with no fuel to reverse its course. Just one shot. But it was incredible. The data revealed a world more complex and active than we ever imagined. I saw ice mountains as tall as the Rockies. Vast nitrogen plains flowed across the surface, constantly renewing that frozen world. A thin atmosphere escaped into the void, forming a ghostly tail caught in the solar wind. 5 moons kept it company. Charon is so massive that it looks more like a partner than a simple moon. This wasn't a dead rock. It was a dynamic, fascinating world with a heart that was still beating with geological life. It was alive with movement. After the encounter, the probe drifted deeper into the icy graveyard of the Kuiper Belt. In January 2019, 13 years into its journey, it found Arakoth, a strange, lonely rock floating in the deep dark. It looked like 2 spheres fused together in a gentle kiss from the very beginning of our solar system. That was the most distant encounter we have ever achieved. The probe was 4 billion miles from the home I left. Light takes 6 hours just to cross that gap. And still, New Horizons keeps drifting further away. It is still talking to us, still exploring. Eventually, it will leave our sun behind and enter the interstellar silence. It will join the Voyagers as our messengers. Deep space exploration demands a kind of patience that few back home understand. Nearly a decade of travel for one brief moment. Then, years more drifting into the frozen heart of the belt. 18 years of service and counting. It will keep going until its nuclear heart finally stops and the power runs dry. How do we survive these long journeys? Near the sun, our solar panels work just fine to keep the lights on. Sunlight is abundant here. Even on Mars, With 43% intensity, those rovers can soak up enough juice to work, but push further out, and the light fades fast. By Jupiter, you are only getting 4% of what hits Earth. At Saturn, it is 1%. By Neptune, it is a ghost. Solar panels become useless weight in the dark. To survive the deep freeze, we rely on RTG's nuclear generators that thrive where the sun cannot reach. Think of them as nuclear batteries. Radioactive plutonium-238 decays inside, bleeding off precious heat into the cold. We turn that heat into power. No moving parts, nothing to jam, just pure, reliable energy in the void. It only dies when the fuel does. Plutonium-238 takes 87.7 years to lose half its strength. After that long, the power drops by half. The heat fades, and the electricity slows down to a final trickle. For missions lasting decades, this slow fade is something we can plan for. It is predictable, even out here. We know exactly how much time we have. The Voyager probes have survived on this nuclear heart for nearly 50 years. They are weaker now, but they still have enough spark to talk to us from the very edge of the abyss. Back home, engineers are shutting down every extra light to save what little power is left in the tanks. They killed the heaters. Parts of the probe are freezing solid as instruments go dark, one after the other. Only the vital organs remain alive. They should keep breathing until the late 2020s, fighting the cold every step. Then, after 50 years, the silence will take them. But they will keep drifting through the dark, forever. Cold and dark, they carry our golden records a message in a bottle for anyone who might be watching the stars. Cassini relied on that same nuclear fire for 20 years, from its launch until its final plunge in 2017. New Horizons is still humming along 2 decades later. It has got at least another 10 years of life left. This tech is our lifeline. But these generators are expensive, and the politics behind them are messy and complicated. We get this fuel from nuclear reactors, but production in the States stopped way back in the late 80s. For a long time, we had to look to Russia to keep our dreams of exploration alive. We started making it again in 2013, but we are running low. There is simply not enough to go around. It is a bottleneck. We have to hoard the fuel, choosing only the most vital journeys to receive the precious isotopes. Some of my fellow explorers saw their missions die before launch because the fuel tanks were simply empty. That is the reality out here. It is not just the distance, it is the scarcity of everything we need, especially when that resource is plutonium. We fight for every dime and every launch window. We must prioritize because we simply cannot do everything at once. You and I have to ask, are we truly stuck with these long travel times forever? Or could we develop technology to reach those distant planets faster? The answer is messy. Up here, it all comes down to energy. To move faster, I need more power. But more power means more fuel, and that means bigger rockets. Those cost a fortune. Eventually, the price tag just stops us cold. These chemical rockets strapped to my seat, they have limits. They just burn fuel and spit fire out the back to move me. Thrust depends on how fast that exhaust exits. Right now, these engines only hit a few miles per second. It is barely enough. That caps my top speed. If I want to cross the void faster, I am going to need a totally different engine. Nuclear thermal rockets are the big dream. Instead of fire, a reactor would cook my propellant to temperatures that would melt anything else. That scorching gas would blast out the nozzle, shoving me forward with incredible force. These engines could double my exhaust speed compared to chemical ones. That would slash my time in the dark significantly. A 7 to 9 month slog to Mars could be cut down to just 3 or 4 months. Imagine that. Jupiter would go from a 6-year trek to just 2 or 3. NASA and other space agencies have been eyeing this tech since the 1960s. We built the reactors and fired them up on Earth. The math holds, but I have never seen one actually fly out here. The hang-up is not the physics, it is the politics. People are terrified of launching a nuclear reactor over their heads. What if it blows up on the pad and rains radiation? What if the core fails while I am out here? Those fears have kept these engines grounded, no matter how much they could help me explore. Then there are ion drives. They use electricity to turn xenon gas into a high-speed stream of particles. Electric fields whip those ions out the back at massive speeds. The problem? The push is incredibly weak, like a whisper. I could never launch from Earth using one. The thrust is way too puny to fight the planet's gravity. But out here in the void, that tiny nudge adds up. I can keep an ion engine humming for years at a time. It slowly builds my speed until I am flying. The Dawn mission used this to reach the asteroids Vesta and Ceres. Deep Space One did the same thing to prove the tech could actually work. They worked, but they are slow. They are perfect for robots that are not in a rush and just need to travel light. When my life is on the line, slow won't cut it. Maybe a solar sail? It is just a massive, shiny sheet. Sunlight hits the sail and gives me a tiny shove. It is a force so small you would hardly feel it. But without air to stop me, that nudge gets me moving fast. Best part? I do not need to carry a drop of fuel. The sun powers me for free, but the pickup is agonizingly slow, and it only works if I stay close to the light. Back in 2019, LightSail 2 proved this could work while it was orbiting my home planet. It worked, but for me to reach other planets, the sail would have to be enormous, and I would need a lot of patience. We are talking way more patience than I already have out here. To really haul across the solar system, we need something wilder, like riding a sequence of nuclear explosions, literal atom bombs. They called it Project Orion back in the 50s. It was as crazy as it sounds. The math says it is incredibly fast, but the politics and the fallout risks stopped it before it could ever launch. Fusion rockets could be the holy grail, insane speed and massive thrust, if we can ever get the reactors to actually stay on. But fusion has been 20 years away, for the last 70 years. I am still waiting for that breakthrough. Antimatter could push me near the speed of light. But making that stuff and keeping it is nearly impossible and costs a fortune. We can make a few atoms of it in labs, but not enough to move a ship like mine. If it touches anything, it vanishes in a flash. Storing it safely is a nightmare I don't want to face. Honestly, I am probably stuck with these long flights for the foreseeable future. Maybe nuclear thermal rockets could finally cut my travel time in half. That would change everything. 4 months to Mars instead of 9, 3 years to Jupiter instead of 6. I could handle that trek. But we aren't talking about light speed. I won't be reaching Mars in days or Jupiter in weeks anytime soon. The physics are brutal, and the engineering is harder. Exploring the deep dark is still going to take a lot of waiting. It takes decades of work to pull this off. We need a commitment that lasts longer than any politician's career. I need people on the ground who will spend their whole lives on a mission they might never see finish. But look at what we have already done. We have touched every planet. I am watching ships that have lasted out here for decades. We have the brains and the grit to keep pushing further into the black. It isn't a question of if we can. I know we can. The real question is, do we have the heart to keep going? Will we keep funding missions that take years to pay off? Can our scientific institutions sustain this long-term research from up here? Will we train the next generation of engineers to step into my boots and continue this work? Those are political questions, not technical ones. From my window, I can see the planets aren't going anywhere. They will be there, whether we explore them or not. The real question is if humanity stays curious and committed enough to keep looking. Let us think about what these travel times mean for our search. To me, the most exciting part is that life might exist elsewhere in our system. Not intelligent life, probably, but microbes, simple organisms surviving in extreme environments I witness every single day. Mars is the obvious target. Billions of years ago, liquid water flowed across the very surface I am watching. Rivers and lakes once existed there, maybe even oceans. We know water is the absolute key to finding life. Where there was water, there might have been life. If it started then, it might still be hiding underground, protected from the surface in underground aquifers or hydrothermal systems. Finding life on Mars would be the most profound discovery in history. It would prove Earth isn't unique, showing life can start anywhere independently. The universe might be teeming with life in places we have not yet explored, but the search is agonizingly slow. From launch, it takes 7 to 9 months just to reach the planet. Then the rover spends years crawling the dust, analyzing soil and rocks, hunting for any tiny sign of life. Right now, Perseverance is down there caching samples for a future mission to bring back home to Earth. But that return mission will not launch until the late 2020s. It will take 7 to 9 months just to reach the Martian surface. It will collect those cached samples, launch from the surface, and spend another 7 to 9 months on the long journey back home to Earth. Best case scenario, we won't have those samples in our labs until the early 2030s. That is more than a decade from today. And that assumes everything goes perfectly. Out here, I know that almost never happens in space exploration. Hunting for life is a slow, tedious process. Every mission I see builds on the one before it. Each discovery brings new questions for the next crew. We are making progress, but it is measured in decades, not months or years. Then there is Europa, orbiting Jupiter. It has a massive ice shell hiding a dark, deep ocean underneath. Jupiter's gravity keeps that water liquid through tidal heating. And where there is water, I hope for life. But it is so far. It takes 5 to 6 years to reach Jupiter, then months to study Europa. NASA launched the Europa Clipper in October 2024. It will take 5.5 years in deep space before arriving in April 2030. It won't land, but orbit Jupiter and make close flybys of the Moon, using instruments to peer through the ice and into the ocean below. We will hunt for organic compounds and water vents on the surface, trying to determine if that hidden, alien ocean could actually support any form of life. We won't get final answers yet. This mission is just a scout, a way for us to see what we're facing. It tells us where to look next. Landing on that ice would require a mission much more complex than this. That lander hasn't even been designed yet. It's still just a dream, far from being launched into space. It could be decades before we have the money or technology to land there. And then there is Enceladus, one of the moons of Saturn. Enceladus has massive geysers erupting from its south pole. They spray water, ice, and organics right into the void. I've studied how Cassini flew through those plumes and analyzed their composition from the data they sent back home. Those plumes hold water and organic molecules, the energy sources life would need to survive out here. It has everything needed, but it's 7 years away. No mission to Enceladus is even being developed right now. It might be 20 or 30 years before we send a dedicated mission to study Enceladus and search for life in those waters. This is the frustration of my job as an astronaut. The most promising worlds are far away, and reaching them takes years of travel. Research takes years. Funding takes even longer. A single mission can easily span 40 years from the initial concept to the final results I see. That is an entire career, a huge chunk of a human life. But that's what this search demands. It takes patience and commitment across generations to answer questions that might stay unanswered for many decades. Now, let me take you back to what we touched on earlier. Think about the mental toll of long-duration travel. For the robots I work with, time means absolutely nothing. The ship doesn't care if the trip takes years. It doesn't get lonely. It doesn't miss home the way I do. But for me and my crew, psychology is the real battle. Most stays on this station only last 6 months. Some stay for a year. Polyakov went for 14 months, the longest any of us has ever spent up here. These flights prove how hard isolation really is. Being trapped in a tiny can with the same people is exhausting. I can't just go outside. There is nowhere to run. If I have a conflict with a crewmate, I am stuck with them. We are chosen for our mental stability. NASA trains us for years in teamwork and how to resolve every heated argument. I speak with psychologists on Earth regularly, but it is still hard. The sense of isolation up here is absolutely crushing. Even with a steady link to mission control, I miss my family. I ache for fresh air and actual green grass. I miss the sting of rain and the wind on my face. There is zero privacy up here. Some of us adapt. Others just count the seconds until re-entry. Now, imagine a Mars mission, 7 to 9 months of drifting through the dark. I would be in a module much smaller than this station. No resupply ships, no emergency evacuation if things go sideways. If I have a medical emergency, my crew has to save me. If someone snaps mentally, we are their only support system. No help is coming. You and I would land on Mars and spend 18 months on that red dust doing research. We wait for the planets to align for the trip home. Then another 7 to 9 months staring at the stars. The total mission time is nearly 3 years. That is double the time any human has ever spent out here in the black. For Jupiter, it is 5 to 6 years each way. Saturn, we are talking 15 to 20 years of my life. These timelines are beyond anything we have tried. I don't know if a human mind can stay sane for that long. Maybe with the right training and support, we could handle a decade in deep space. I like to think we could. Or maybe my brain has a limit, a point where isolation finally breaks something fundamental inside of me. Maybe the stress gets too heavy, the boredom too thick, and the silence from Earth just becomes too loud to bear. We won't know until I go. But going means gambling with my own mind. I might not come back the same. This is the ethical dilemma. You and I have to ask, Is it right to send me on a mission that might break me? Even though I volunteered and know the risks, there are no easy answers when you are staring into the abyss. For now, we let the robots go. They don't have feelings. They don't get lonely out here in the dark. They can drift for years without suffering. They work in total silence without stress. They are the perfect scouts for the void. But a rover can't make decisions like I can. A geologist on the Martian surface could work 10 times faster. I can spot a strange rock and make an intuitive leap. I can adapt to surprises that would crash a robot's software. There is a reason we still send people to the deep ocean. My judgment and creativity simply cannot be replaced. It is the same on other worlds. We face a choice. Robots are patient, but they only see what they are told to see. We are capable and adaptable, but our bodies can't survive the long journey out there with the tech we have now. Maybe future tech will fix this. Maybe we will finally figure out how to put me into a deep, cryogenic sleep. I could just sleep through the entire trip. They would put me in hibernation right after I clear the atmosphere. I would wake up at the destination. To me, the years of travel would feel like a quick nap. It is a sci-fi staple, but for us, it is just a dream. We have no idea how to do it safely yet. We don't know how to stop ice crystals from shredding my tissue, or how to keep my heart beating for years. We don't know how to wake me up after years of slumber. Sure, some animals hibernate for a few months, but that is not true stasis. Their bodies just slow down. They still need food reserves to survive the winter. Scaling that up for a human is a massive hurdle. Maybe someone will solve it one day, but not today. Maybe in 100 years we will have the tech to put explorers to sleep for the long haul. But right now, we are not even close. If I travel to another planet, I have to be wide awake. I will experience every single second of that void, fighting the mental demons that come with the silence. This is exactly why the travel time is so critical. It is not just about the clock on the wall. It is about what that time does to me, to my soul. Now, let's look at the costs together. Rocket science is expensive, and every extra day I am out here, the price tag just keeps climbing. My ship has to be built to endure, and the team on the ground has to be paid to watch me. Every day I am in orbit. A room full of engineers and scientists is watching my every move and telemetry. For a Mars run, you need that team for 9 months straight, plus all the planning and data crunching. If I go to Saturn for 7 years, that team has to be there every single day of that journey. That is 7 years of payroll and bills. The Cassini mission cost about $3.26 billion. I look at the console and realize it took over 20 years to get here. At least $3 billion, roughly $160 million per year. It sounds like a fortune, but peering out at Saturn, Cassini's payoff was worth every single penny. Thousands of images flooded back to Earth. We rewrote every textbook about these rings and those distant, icy moons. It completely shattered everything we thought we knew about the deep solar system. If you and I calculate the cost per secret revealed, Cassini was a steal. But out here, things go wrong. Every crash is a nightmare. We lose the science, sure, but we also incinerate decades of human investment. This is why I double-check every seal. Success isn't just about science, it's justifying why we are even here. We must prove to everyone back home that this void is worth exploring. Every win makes the next journey possible. One mistake makes the next mission impossible. It forces us to play it safe, sticking to what we know works. We avoid the bold, risky designs that could change everything. When billions are at stake, fear of failure is only human. When you dedicate your whole life and billions of dollars to one shot, you want a guaranteed victory. But playing it safe keeps us grounded. Think about the thrill of finally bringing Martian soil back to Earth. Descending onto Europa or drilling into hidden oceans, that is where we push the absolute limits of human technology. If these bold steps fail, the price is devastating. So they get shelved, replaced by something easier and cheaper. It is a strange paradox. We crave the massive discoveries, yet we are terrified of the risks involved. Since the stakes and costs are so astronomical, the most ambitious dreams spend decades just waiting for approval. We have talked about Mars samples forever. Finally, a launch is set for the late 2020s. I can almost see it. That is 40 years of planning. We have been dreaming of sending people like me to the Red Planet since the 1960s. Yet, we are nowhere near. Deep space missions take even longer. They are just too dangerous and too expensive. Why is our progress so slow? It isn't just the technology, though that is definitely a hurdle out here. It is because we struggle to commit to the long haul. We lack the fire to fund the future. Back on Earth, space must fight for scraps against healthcare, schools, and the engines of war. Floating here is incredible, but how do I tell a sick child that my mission matters more than their doctor? So, we work with what we have. We balance our thirst for discovery against the cold reality of a budget. We have to prove our worth. But how do you justify a mission that won't finish for 30 years? The people signing the checks won't live to see the end. Politicians focused on next year hate long-term bets. This is the real barrier. The universe operates on scales that simply do not match our tiny human timelines. You and I live in a world obsessed with annual budgets and quick election cycles. But out here, we think in generations. Bridging that gap requires a vision that most people can't even imagine. Yet, we have survived. NASA has been pushing forward for over 66 years. Other agencies have followed for decades. These institutions have endured. They have weathered political storms and leadership changes without ever stopping their climb. Through every budget cut and crisis, they kept looking up. They kept sending us out to these distant, lonely worlds. They keep pushing the boundaries. This sheer persistence might be the greatest thing humanity has ever done. We have built something that outlives us. These projects last longer than any single career or even a lifetime. We pass the torch from one generation to the next. This is the only way we reach the stars. It isn't about one hero. It's about a massive, sustained effort that never blinks, even when the lights go out. People planned my journey 20 years ago. They won't see the final results until the 2040s. We stand on the shoulders of giants. We are just laying the tracks for whoever comes after us. It is a shared hunger for truth that lasts much longer than any individual life ever could. When you think about the years it takes to get here, realize it isn't just a technical puzzle. These missions are grueling tests of our patience and our will. Every craft that arrives safely is a victory for our species. It proves we can finally think long-term. Every new secret we uncover proves that we can conquer our own impatience and keep moving forward. We can reach for goals that take a lifetime. That is the true power of our curiosity. You and I are part of a journey that transcends time, proving we can achieve anything we imagine. Up here in the dark, I see the ultimate lesson. It isn't just about what we found on Mars or Saturn. It is what we have learned about our own nature. We are capable of incredible patience, committing to goals that outlast our lives, and uniting to do something legendary. Those planets aren't going anywhere. They will circle the sun for billions of years, whether we ever touch their soil or not. The real question is if we have the vision and the grit to keep pushing. These travel times are fixed by the stars. Cold physics decides how long it takes to reach a new world. We can't cheat the math, at least not yet, but we can shift our perspective. We can embrace the long wait and commit to missions that span decades of our lives. We must build things that last for generations, training the next wave of explorers to take over when we finally step back. That's how you really explore a solar system. Not with brute force or raw speed, but through pure, stubborn persistence. We have to be patient enough to wait years for a signal and committed enough to fund missions that won't show results until we are gone. We need the vision to value knowledge that has no instant payoff. Out here in the black, you realize those travel times are brutal. They are soul-crushing by human standards, but we have proven we can endure. We have put our eyes on every planet and kept missions running for decades. Right now, we are mapping out missions that will spend years drifting through the black. Every probe, every grainy photo, and every tiny measurement rewrites what we know about this vast universe we call home. That wisdom is worth the wait. It's worth the years of drifting in the void, the decades of dedication, and the entire careers spent talking to machines in deep space. This is simply who we are. We are born explorers. We stare at distant lights in the dark and can't help but wonder. We build ships to find the truth for us. We wait years for them to arrive and whisper back what they've seen. Then we stand in awe of the secrets we uncover. The journey is long, but we have the time and the patience. The whole system is waiting. Let's look closer at what these trips really feel like. The numbers tell one story, but the human experience out here, that is something else entirely. Think about the team talking to Curiosity right now. That rover touched down in the red dust back in August 2012. It has been crawling for over 13 years. That is 13 long years of constant, daily work. Every day, a squad of scientists and engineers huddles to plan its next move. They pore over images and data sent from the previous day. They debate every rock and shadow, deciding where the rover rolls next. Every instrument choice is a heated discussion about the mission's future. They craft the code that acts as the rover's brain. Then, they beam those commands across the empty space to Mars. Those signals fly at the speed of light, taking anywhere from 4 to 24 minutes to arrive, depending on where the planets are hanging. Curiosity wakes up, does its job alone, and beams the results back. That data takes another 4 to 24 minutes to reach home. By the time we see what happened, it's already old news. The rover could have finished its work 20 minutes before we even knew. We call it the Mars time delay. It dictates every single move we make with these machines. You can't just joyride a rover. The lag is far too dangerous. By the time you even see an obstacle, the rover has likely already crashed into it. So, the crews live on Martian time. A day there, called a sol, lasts 24 hours and 39 minutes. That is 39 minutes longer than our days here. After 1 week, Martian time and Earth time are nearly 4.5 hours out of sync. Give it a month, and you're a full day off. The teams have to shift their entire lives every single day just to stay synchronized. Today, you clock in at 9 a.m. Tomorrow, it's 9:40 a.m. And things start feeling weird. The next day, it's 10:20. Your schedule just keeps drifting later until you're suddenly working in the dead of night. Then it loops back to morning. It's violent for the human body. Your biological clock is essentially being torn apart. You're never okay. You're permanently jet-lagged. Some of us even start dreaming that we're actually standing on that red surface. We see those dusty landscapes through the rover's eyes. The line between being on Earth and being on Mars just disappears. We spend so much time obsessed with Mars that it feels more real than the cold mission control room where our bodies actually sit. This lasts for months. Some of our teams have lived on Mars time for 4 months straight without a break. It's pure exhaustion, but it's the only way to get every bit of science out of that machine. When you're running a $2.5 billion mission, you don't waste a single second of sunlight on another planet. Now, imagine what it's like when you put us on the ship. We'd be living on Mars time naturally out here, but our friends back home would face those same brutal shifts. But instead of a robot, they'd be keeping us alive. The stakes would be terrifying, every decision critical, and the stress almost unbearable. I wouldn't just be out there for months. I would be on that surface mission for 18 months or more. The team supporting us has to stay sharp for over a year, working strange hours while totally out of sync with Earth time. Staying alert for a crisis is one thing for a few months, but asking us to stay that vigilant for a year? That is heavy. It is a hidden tax of long-haul spaceflight, the sheer human grind required to keep things running once we actually arrive. Let's look at something you and I rarely consider: the aging of our ships. At launch, every single nut and bolt is brand new. Initially, everything is tested and perfect. Then the void hits. Cosmic radiation starts hammering the hull without a single moment of rest. High-energy particles shred the electronics, hunting for a failure. The heat is worse. Sunlight cooks our exterior at hundreds of degrees. In the shadows, it plunges to hundreds below zero. This thermal whiplash makes the metal skin groan, expanding and contracting constantly. Gaskets turn brittle. Lubricants freeze up or just vanish. Meanwhile, dust chokes the solar panels, slowly starving the mission of power. Batteries fade, gears grind down, and out here, there is no roadside assistance to swap a bearing or unstick a jammed latch. One break, and it is over. We either bypass the failure or the mission dies. Redundancy is our only shield against the dark. We pack layers of backups. Take Voyager. It has got spare computers, transmitters, and thruster controls just waiting for their turn to fail. When one fails, the ship flips the switch. But eventually, the spares run dry. You cannot predict every disaster in the deep. Spirit, a rover that touched down in 2004, found itself buried in deep Martian sand by 2009. Engineers fought for months to free it, but the wheels would not budge. Its panels were trapped, tilted away from the sun. It could not catch enough light to survive the Martian winter. Spirit just froze. It never opened its eyes again. We did not lose it to a short circuit. It died because it was physically trapped in a place where survival was impossible. Then there was Opportunity, Spirit's twin. She survived 14 years, until a planet-wide dust storm blotted out the entire sky. In 2018, the dust choked its panels. The rover entered a deep sleep, waiting for the sky to finally clear. But the dark lasted too long. The batteries bled dry. When the dust finally settled, our little explorer could not wake up. We shouted into the void for months, hoping for a ping. Nothing. The Martian cold likely shattered something vital inside her. The batteries were past the point of no return. After 14 years, Opportunity's luck finally ran out in the silence. They were only supposed to last 90 days. Instead, Opportunity gave us 14 years, and Spirit gave us 6. But time is the ultimate predator out here. Even the mighty Cassini met its end when the fuel gauges hit empty. After 13 years circling Saturn and its moons, the fuel was gone. The ship was finally running on empty. Without fuel, Cassini was a ghost ship adrift. It was only a matter of time before it slammed into a moon. We could not risk contaminating moons like Enceladus with Earth microbes. So, NASA dove Cassini straight into Saturn's crushing atmosphere. On September 15th, 2017, Cassini took its final plunge. It screamed back data until the very end. The pressure and heat finally shredded the hull. A violent ending, sure, but it was a choice, not an accident. It was a controlled conclusion rather than a slow decay into failure. That is how we end most missions out here. It is usually one of two things: a sudden, catastrophic break, or the slow, agonizing exhaustion of fuel and power. We pull the plug ourselves before the void claims the ship. Almost nothing keeps working forever in this environment. Time, radiation, and the vacuum. They always win. You and I have to design for a very long fight. We have to calculate the clock after arrival. If the journey to Saturn takes 6 years, we need much more life in the ship. To pull off a 4-year study, your vessel needs to be rock solid for at least a full decade. We leave room for the unexpected. Cassini was built for 11 years but fought through 20. That is the dream. That kind of engineering is rare. Most ships do not double their lifespan. It is a massive weight on our shoulders during design. We want ships that last forever, but every extra shield adds weight. Every backup adds complexity. It is a dangerous balance. It is always a gamble. A stripped-down, cheap probe might hit its deadline and then just die immediately. A heavy, expensive build might keep talking for decades. It all depends on your budget and how much risk you can stomach. We usually aim for the robust, expensive builds. We want missions that go the distance and bring back every scrap of data. The science justifies the price tag, but it means we do not get to fly very often. Every launch is precious. Other agencies or private firms take the opposite path: cheaper. Faster ships with a much higher chance of failing. It lets them try more often, throwing more at the wall to see what sticks. There is no single right answer out here. In the end, you and I are both fighting the same enemy: time, the time to get there and the time to finish. Looking out at the void, I see it clearly. Every bit of data, every plan, it's all bought with years. In deep space, time is the only currency. And time is the one thing I can't get more of. You and I should examine something truly haunting about these long-haul missions. The people controlling my craft today often aren't the ones who built it. Just think about that for a second. The New Horizons mission to Pluto launched in 2006. It didn't arrive until 2015, nearly 10 years of silent drifting. Some scientists who dreamt up the mission in the 1990s were already retired by the time the probe finally reached Pluto. Engineers moved on to new lives, yet the mission never stopped. Fresh faces stepped in to guide a machine they didn't create. Kids who were in high school when it launched grew up to become the lead researchers analyzing the secrets Pluto finally revealed. Students who were just starting college when we built it are now the specialists commanding us from deep in the Kuiper Belt. These missions span generations not through bloodlines, but through a passing of the torch from one career to the next. People at every stage of life, all pouring their souls into one singular, distant goal. It's rare to see that anywhere else. Most jobs don't stretch across decades. You start, you finish, and you leave. But space? Space doesn't work that way. A single planetary mission can swallow an entire professional life. You give your whole self to just one ship, one world. You start as a student on early designs, survive development as a postdoc, and eventually become the scientist watching it fly. You age from lead operator to professor emeritus. still obsessing over the final data packets sent back across the light years. 40 years tethered to one machine. It's not just a contract. It's a deep, frighteningly intense bond with the unknown. This isn't just a paycheck for the team on the ground. It's their life's work, decades of spirit, poured into a single endeavor. When Cassini ended its mission in 2017, I heard about the scientists weeping. It felt like losing a family member. They had spent 20 years on that mission. Some had known nothing else their entire adult lives. Then, suddenly, it was over. The craft was gone, incinerated in Saturn atmosphere. Their life's work was finished. A success by every measure, but a brutal goodbye nonetheless. Cassini did everything we asked and more, but knowing it's over doesn't make the silence any easier to bear. It's a profound loss of identity, that emotional gravity between a human and a machine out here. It's real and powerful. We form bonds with these explorers. It's not romance, it's a long-term partnership forged across the vacuum of space and time. When you live with a machine for decades, you celebrate its wins and stay awake at night worrying about its glitches. You mourn when the signal dies. Look at Opportunity. The world followed that little rover's Martian journey for 14 long years. When the dust storm swallowed it and the radio went silent, a wave of grief hit everyone back home on Earth. It wasn't just NASA. Regular people who had never touched a telescope felt the sting. They'd lived through every image it sent back. They read every update, feeling a strange connection to that lonely robot on a red desert. When it went dark, they felt the loss. Messages poured into NASA from every corner of the globe. Thousands of people sharing their sorrow and honoring what that rover achieved. Some joked it finally earned a nap after 14 years of trekking, but beneath the humor, you could feel the genuine heartache. People truly cared. That machine, millions of miles away from me, represented our purest instincts, curiosity, the need to explore. It was more than a robot. It was our scout, our lonely representative on the frozen, dust-choked plains of Mars. It was our eyes and our hands. When it died, our physical link to that world snapped until the next rover landed. Then the cycle repeats. This is the human side of the void, the parts they never write down in the technical manuals, the raw emotional cost, the devotion, and the terrifying sense of purpose that comes from chasing goals that will outlive your own heartbeat. The people guiding us through the dark don't do it for the money. Believe me, the paychecks aren't exactly astronomical. They could earn double in the corporate world. They don't do it for fame either. Most work in total, quiet obscurity. You'll never know their names. They do it because they believe expanding the light of human knowledge is worth the sacrifice. You and I both know that being part of something that outlasts us is what gives a human life real meaning. The crushing wait times don't scare them off. Honestly, that requirement for absolute patience is exactly what draws a certain soul in. They're people who can think across decades. They don't need a win today. They're working for a victory 10 years from now. These are the people who truly make this possible. Not just us astronauts, though I know we get the glory up here. It's the engineers and the support staff on the ground who keep us alive, designing and operating these ships for decades. Without their endless patience, we would be blind. Every stunning shot of a Jovian storm exists because they never gave up. Every Martian rock analyzed and every magnetic field measured is thanks to someone who spent half their life making it happen. You and I must recognize this, the years of life invested in the stars. The patience to wait years for a signal, the grit to keep a mission alive for decades, and the soul to dedicate a career to a single distant world. These light years of travel test us. They test our resolve, our focus, and our ability to see past the horizon of our own lives. I have watched us pass this test repeatedly out here. We have proven we can wait. We can dedicate decades to a single goal. That is worth celebrating because it says something mysterious about human nature. We are not just slaves to the next immediate thrill. We are capable of profound patience, of working toward goals in the dark, of caring about things that will never benefit us directly. We are the ones planting trees for a shade we will never feel. We build great cathedrals we will never see finished. We launch spacecraft into the void, knowing the data will not arrive for years. This long-term vision is one of our greatest strengths. It is what allows us to face generational threats like climate change. It lets us build institutions that outlast our own fleeting lives. And it is the only way we can cross the terrifying gaps of the solar system. The planets are so incredibly far away. Reaching them takes years of silence. Studying them takes even longer, but we endure it because the truth is worth the wait. Searching is in our blood. Understanding our place in this vast universe matters. We are bound by time and the laws of physics. We cannot shrink these distances or make our ships fly faster, not with the technology we have in our hands today. But we can change how we perceive time itself. We can treat patience as a virtue rather than a heavy burden to carry. We commit to these distant targets knowing we may not live to see the end. We work for the future, not for ourselves. This is the mindset that makes space travel possible, and it is a perspective worth cultivating in every other area of our lives, because most things worth doing take time. Mastering a craft takes years. Building a career takes an entire lifetime of steady work. Raising a child takes 20 years of quiet devotion and commitment. Creating lasting change in our society takes generations of effort. We live in a world obsessed with instant gratification and speed, but the truly valuable things in life are never fast or easy. They demand sweat, silence, and patience. Space exploration teaches us this lesson in the most brutal and dramatic way possible. You cannot rush a journey to Saturn. The transit takes 7 years. No matter how anxious you are, you must wait in the dark. You learn to love the journey, the endless drift between the stars. You find value in every tiny bit of incremental progress. Every mile reached, every thruster fired, every system check that stays green while the void screams outside the hull. These minor victories accumulate over years into monumental achievements. This is true in the cockpit, and it is true down on Earth. Major accomplishments are always built from small, daily efforts sustained over long periods of time. The years it takes to reach the planets remind us of this truth. They force us to be patient and value persistent commitment. And in doing so, they make us something more. Not just explorers of the void, but better versions of ourselves. When you look at the clock and see years of travel, remember those aren't just numbers. They are deep tests of human character. These challenges push us to be more patient and committed to the distant future. Every mission that succeeds after years of travel proves we can pass these tests, that we can wait when the universe demands it, that we can strive for goals that will only be finished long after we're gone, that we can work together across decades to accomplish extraordinary things. The solar system is a vast and lonely place. The paths are long, but we are walking them, one quiet mission at a time. We aren't just mapping the empty space. We are finally discovering exactly what our species is capable of. Our capacity for waiting, our will to commit, our drive for knowledge, even when the pursuit takes decades of our lives. This is who we are, at our absolute best. And these long journeys into the unknown bring that out in us.